Welcome back everyone. In this lecture I will actually give you some useful definitions that will be very useful later in the theory, and we will also see some examples of normal subgroups that naturally arise from given groups. Okay, so let us begin with the following definition, that is the center of G. So, as before, G is given group. Okay, so this is already fixed notation. So, then given a group G, so we define what is called the center of G, which is denoted by Z of G. Okay, so this is those x in G such that those x that commutes with all y in G. Okay, all other elements of capital G. So, x y should be equal to y x for all y in capital G. So, those elements that commute with all elements of capital G, they form the center of capital G. So, it is easy to check this center is indeed actually a normal subgroup of G. Okay, so this is the claim, the center is indeed normal subgroup of G. So, how one can verify this? So, you can see that first of all it is a subgroup. So, that is something easy to verify. So, let us start with two elements x and y inside center of G. Using the characterization, it is enough to prove that xy inverse is in the center of G. So, let us see what happens if we apply xy inverse and then choose some random element z and then see what happens. So, for any z in capital G, we can see that xy inverse z is nothing but x y inverse z, but since y is actually commuting with x, so it is a simple calculation to see that y inverse is also commuting. Okay. So, since y z is exactly same as zy, by pre-multiplying and post-multiplying by y inverse, you can see that y inverse yz y inverse is same as y inverse zy y inverse. So, which gives z y inverse equal to y inverse z. Okay. So, these two terms get cancelled, gives identity. So, then you get z y inverse, and these two terms get cancelled and you get identity. So, that gives y inverse z. So, that means y inverse z is same as z y inverse. So, this becomes x z y inverse. So, which is exactly equal to x z y inverse. So, now you can see that x z is same as z x because x is in the center. So, then it gives z x y inverse. So, which is same as z x y inverse. So, because we have chosen z to be some arbitrary element in capital G, so we see that x y inverse commutes with all elements of capital G. So, that means x y inverse is again inside your center. Okay. So, that proves that center of G is indeed subgroup of G. So, now we want to prove that center of G is indeed normal subgroup. Okay. For that we can use any one of the definitions. For example, if we start with any G in capital G, then if I compute G into Z of G. So, since all elements of Z of G commutes with this G, so you can see that this is exactly equal to Gx x in Z of G. But for any x, we know that for any x in Z of G, Gx equal to xg. So, this set is same as xg when x is in Z coming from Z of G. So, that means this is exactly equal to Z of G, Z of capital G times small g. So, this proves that G Z of G is exactly equal to Z of Gg for all G in G. So, that means what? That means this Z of G is indeed normal subgroup of capital G. So, from this abstract definition, so we can see that the center is always a normal subgroup of capital G. Of course, given some example of non-abelian group, it will be actually very hard to compute what will be the center, but we will try to compute center for some specific examples later. Okay. So, and it is easy to see some properties of center. For example, if G is abelian, then you can easily see that the center is being actually full. So, it is actually a characterization of abelian group. If you take G is abelian, then the center is exactly equal to capital G. So, that is by definition. So, this is maybe I will leave it to you to check. So, this is I will leave it as exercise. Okay. So, this is something interesting normal subgroup of capital G. Okay. And let us see some examples, very specific examples. So, for which we get normal subgroups. Okay. So, like I said, so one can identify normal subgroups as kernel of group homomorphisms. So, whenever you are interested in producing normal subgroups, you should look for group homomorphisms. Okay. So, that is the best way to actually come up with normal subgroups. So, here some trivial examples. So, if you start with an abelian group, so then any any subgroup will become a normal subgroup. Okay. Any subgroup is normal in G. Okay. So, that is because all elements commutes. So, if you compute G capital H G inverse for any capital H subgroup of capital G, you can see that G H G inverse will be just H. Okay. So, this is something very easy to verify. So, what is advantage? It may sound like a very trivial fact, but this actually kind of allows us to produce new examples from given abelian groups. Okay. For example, one can actually take the group of rational numbers with respect to addition. Okay. So, then if you take for example, this set of integers, again subgroup of integers with respect to addition. So, this is a subgroup inside the group of rational numbers. So, then from our actually construction, one can talk about the factor group Z Q modulo Z. Okay. This is very interesting quotient group. So, this is actually a quotient group or factor group. So, this group is somewhat very interesting group. Okay. So, let us see like how some typical element in this group looks like. Okay. If I take this Q mod Z, okay, what it is those cosets P by Q plus Z, where P by Q is a rational number. Okay. And one can parameterize this P by Q as P is coming from Z and Q is coming from, for example, natural number, and then this mod P and Q. So, they being GCD 1 whenever it is non-zero. Okay, we can choose it to be GCD of this is 1 whenever P non-zero. Okay, so we can actually choose some parameterizing like this, but if you really think about it, for example, if I am interested in, let us say some rationals. Okay. So, if you try to plot the rationals in the real line, you have 0, you have 1, you have 2 and so on, and then -1, -2 and so on. So, the rationals will somewhere lie here. Okay. But each rational number, what we are indeed doing, we are taking this Z translation, that is the coset. Okay. So, if I take a rational number here, let us call it capital X. So, then I am looking at all this integral translation of X, that is my element in Q modulo Z. Okay. So, then as an element, it is a subset of this R, which is all this Z translation or integral translation of this X. So, this X will be there, and then you will be taking this X plus 1 and then this X minus 1 and so on. Okay. So, this is X plus Z, that is X plus N, where N comes from Z. So, this is one element. So this is one element in our Q mod z. Okay. So that is something kind of this graphical interpretation somewhat tells us that what will be an ideal set of representatives for this Q modulo z. For example, one can restrict oneself in between the rational that are there between 0 and 1. Okay. So I am going to write down another parameterizing set. So you can take x plus ez, where x is coming from 0 to 1 and then x is just a rational number. Okay. So this is, if you think about it, this is another set of representatives or the so another parameterizing set for this Q modulo h. Okay. So if we take for example this 0 plus z and then 1 plus z, so we are going to get only z. Okay. That means they are identified. Okay. So this is actually gives us again some geometric interpretation of this Q modulo z. Okay. So to understand that geometric interpretation, one has to identify Q mod z inside R modulo z. Okay. So we have again z being a subgroup of Q, Q being a subgroup of R, where R I am treating it as set of all real numbers with respect to addition. So what we are now trying to do, we are trying to take this quotient R modulo z. So this R modulo z again can be parameterized as x plus z, where x is coming from R. Again using this geometrical interpretation, okay, you can see that if you try to plot it, okay, the elements here, okay, so this is going to be 0, this is going to be 1, this is going to be 2 and so on, here minus 1, minus 2 and so on. So then if you take some x here, then the x plus 1 will lie here, x plus 2 will lie here and so on, and x minus 1 will lie here. So that means, so this thing can be reparameterized as x plus z, where x is coming from 0 to 1. Okay. So that means, so basically all we are doing, you can take this particular segment, okay. So and then each element in this particular segment from close to 0 comma open 1 gives you parameterizing set for R modulo z. And then if you think about it, because 0 plus z is same as 1 plus z, so this gives us this identification of R modulo z with S1. Okay. So R modulo z can be identified with S1. So this is the unit circle which topologically you are identifying 0 and 1. So this has some topological interpretation. So let's not worry about it for time being, okay. But as a parameterizing set, one can easily identify this R modulo z with the circle S1. So that is just you take this closed 0 and open 1, which has same parameterizing. There is a bijective correspondence between closed 0 comma open 1 to S1. So that is all I am saying. Okay. So now if you take these groups, okay, how you add two elements and so on. Okay. For example, let's take this Q mod z. Okay. So this Q mod z, so this looks like, so typical element looks like P by Q plus z. Okay. So then this can be written as 1 by Q plus etc. plus 1 by Q. So let us take P to be positive. Okay. So P is just some natural number, Q is also some natural number. So then this is going to be P times 1 by Q plus 1 by Q and so on. Okay. So let's not put it here. So this is going to be P times plus z. So that means what? That means, so this you are adding 1 by q p number of times, and then you are considering the corresponding coset here. Okay, so that means this is exactly 1 by q plus z, and then in your group you add this 1 by q plus z p number of times. So then you are exactly getting this particular element on the left side. Okay. So now if you think about it, if you take this p by q plus z and then you add this q number of times, okay, again q is natural number. So then what happens? So you add this p by q plus etc. p by q number of times. Okay. So this is you are going to do q number of times. So then what you are going to get? Plus z. So then you can see that this is going to be exactly equal to q times p by q plus z. So that is going to give you p plus z. But p is some integer. So that means this p plus z is exactly z. Okay. So that means if I take this p by q plus z and then add it q number of times, then exactly I am getting z. But z is just 0 plus z, which is the identity element. So this is the identity element in your group q modulo z. So that means the order of this p by q plus z actually divides exactly q. Okay. So I will leave it to actually check, okay, or find. So this is exercise for you. Okay, find the exact order of p by q plus z in q modulo z. Okay. So this tells you that this argument actually tells you that this p by q plus z, it has finite order, and so the similar argument one can actually give as long as q is natural number. So this can be performed, p can be any integer. So that tells you that any element of this group q modulo z, all of them have finite order. Okay. So they all have finite, all elements. So this is the thing that we have proved. All elements in q mod z have finite order. So this is something very surprising thing. Even though the group is infinite, it is actually countably infinite. So each element of the group has only finite order. Okay, that's very surprising. So similar questions can be asked even in the group R modulo z. Okay. So I will leave it to you to think about it, what happens when you take R modulo z. For example, like I said, you can have the parameterizing set x plus z, where x is coming from 0 to 1. So if x is rational, we just observe that it has finite order. So x can be irrational, okay, lying between 0 and 1. If you take x irrational, then you can prove that it must have infinite order in this group R modulo z. Okay. So this is something I will leave it to you to check. So the exercise, find order of x plus z for x irrational in 0 to 1. Okay. So this is something you can try to do. Okay. So now let's see some easy examples. Okay. For example, if I take set of all invertible matrices, n by n invertible matrices over let's say real number. Okay. This is the set of all n by n matrices over real numbers. So then we have very nice homomorphism from this group to R cross. So this is non-zero real numbers. Okay. So, what is that group homomorphism? Sending any matrix to the determinant of that matrix, and it is a fact from linear algebra. If you take product of two matrices, the determinant of AB is exactly equal to determinant of A times determinant of B. So, that means determinant is indeed a group homomorphism from the set of all invertible matrices, that is a group of invertible matrices GLN of R to R cross. Okay. So, then what will be the kernel of this map? So, this map is usually denoted by det. So, the determinant map, the kernel will be those matrices from GLN of R that are having, so phi of A to be identity, but this is the group of non-zero real numbers with respect to multiplication. So, one is the group identity here on the right side. So, in particularly the determinant of A should be 1. So, those are all the elements that makes the kernel. Okay. And as before, we can see that the kernel is nothing but the normal subgroup of this GLN of R. So, it is very interesting subgroup of this the set of all invertible matrices GLN of R. So, again I want to actually emphasize one more example which we have seen already, which is the symmetric group. Okay. But if we take this symmetric group, there is something called sign of a permutation. Okay. So, I want to introduce this sign using some realization of the symmetric group. Okay. This is I would say much more powerful tool that one can actually use in understanding the symmetric group. So, let us see how one can understand the symmetric group in a different way. So, let us take Sn. So, this is the symmetric group. Okay. So, recall symmetric group is nothing but on this 1 to n, that is what we are talking about. So, this is by definition. So, those permutations from 1 to n to 1 to n. So, where In is just 1 to n. So, sigma is a bijective function. Okay. So, this is the group of the symmetric group on n letters. So, now if you think about it, we already fixed some notation for this group. Okay. Given any sigma in Sn, you write the domain on the top and then you write the code the range or the images of those elements at the bottom. So, this is the symbolic way to actually write given element sigma of this Sn. Okay. So, now what I want actually you to realize, so one can identify this symmetric group in a different way. Actually, I am going to talk about group actions later, but we are actually going to this example is one such group action of Sn on some particular space. Okay. So, let us not worry about what is indeed happening, but let us actually just let me give you the explicit elements that are associated with each element of this Sn, and so it is like giving very explicit realization of Sn as subgroup of GLN. So, that is all I am doing. Okay. For that let us fix some notations. So, let us recall what is GLN of R. So, GLN of R, the set of all n by n invertible matrices. So, what I want to do, I want to realize Sn as subgroup of GLN of R. Okay. So, this means we have a injective homomorphism, from Sn into GLN of R. Okay. So, what is the meaning of injective homomorphism? It is a homomorphism from Sn to GLN of R. So, it is a function phi from Sn to this GLN of R, and it is a 1 to 1. This is a group homomorphism plus it is 1-to-1 map. That means it's an injective map. Okay, what is this map? Let me explicitly give you what is this map, and then it becomes, I will leave it to you to check this map is indeed group homomorphism and so on. So, that is again like very trivial. So, to do this let us do one example. Let us take n equal to 3. So, let us look at S3. For example, one can take sigma to be 1, 2, 3 and then let us say 2, 1, 3. Okay. So, what we are going to do? We are going to take this identity matrix. Okay. This is the identity matrix 3 by 3. So, which will be 1, 0, 0, 0, 1, 0 and then 0, 0, 1. So, then what I want to do? So, when the identity element of S3 should be mapped to this identity element, because if you have any group homomorphism, so identity element of the domain should be mapped to the identity element of the range. Okay. So, now if you take this identity element, so this is actually the identity element of the S3 should be mapped to this. So, now for example, I want to map sigma to something. So, where I want to map? What I do? I treat this as, okay, this is actually just a identity matrix. I take the columns of this matrix, this identity matrix. So, there are 3 columns, let us call it E1, E2 and E3. So, I take this sigma and then I apply it on these columns and I just permute them. Okay. So, what is the meaning of that? I take E1, I just replace this with E2 because sigma of 1 is 2. Okay. Sigma of 1 is 2. Similarly, I take E3, E2 and then replace with E1 and then I take E3 and then replace with E3. Okay. So, what is E2? E2 is 0, 1, 0. What is E1? 1, 0, 0 and then E3 is just E3 is just 0, 0, 1. So, I just take this sigma and map it to this matrix. So, which is obtained from identity matrix by permuting the respective columns. Okay. So, now it is clear what we are going to do in general. For example, let me do one more example. So, let us take tau to be 1, 2, 3, let us fix this and then permute these two. So, then tau will be mapped to, so now you can see that this is E1, this is E3, this is E2. So, that means, so this should be mapped to 1, 0, 0, 0, 0, 1 and then 0, 1, 0. Okay. So, this is what it should be mapped. So, now one can also fix row permutations. So, that is also allowed. So, let us fix this column permutation and then work with this. So, it is not a problem. And if you recall from the properties of the determinant, you can see that if you switch 2 columns, okay, ith column and jth column, then one minus sign will come out. Okay. The identity matrix has determinant being 1. Okay. So, then for example, if I take this determinant of, let us say this is I sigma. So, this I sigma is this. So, what is this? How it is obtained? So, you kept E3 as it is and then switched E1 and E2. That means 1 minus should come out. This should be minus 1 determinant of identity. So, which is exactly minus 1. Similarly, if you take the determinant of I tau, okay, I am calling the image as I sigma I tau. So, that is again you switched only, you kept 1 as it is and then you switched 2 and 3. So, it has to be again minus 1. Okay. So, now it is clear what is the homomorphism. You take from Sn to GLN of R, you take any sigma and then you apply the sigma on this n by n identity matrix, which you call it I sigma. Okay. So, basically what is I sigma? I sigma is obtained from this permuting this column vectors you take E sigma 1, E sigma 2 and so on E sigma n. Okay. So, now if you think about it, okay, if you apply I sigma tau, so then it will become exactly E sigma tau 1, E sigma tau 2 and so on E sigma tau n. Okay. So, now so this is just applying first tau and then applying sigma on this. Okay. So, if you just think about it, so this is just applying sigma tau on identity. Okay. So, this is just the product of, okay, I sigma I tau. So, I will leave it to verify this. Okay. This is something easy to verify. So, that is, it is indeed a group homomorphism. So, now if you think about it, so then what is the sign? So, the sign of sigma, I want to define it to be determinant of this I sigma. So, this is my definition of the sign. Okay. So, since determinant is indeed group homomorphism from GLN of R to R cross. Okay. So, now if you compose two group homomorphisms, that is first determinant and then this this sign. Okay. This is let us call it, okay. So, this is the embedding. Okay. Let us call it iota. Okay. So, if I take this iota and then the determinant, the composition of these two. So, both are actually group homomorphisms. So, the composition will be group homomorphism. So, this map we call it the sign map. Okay. So, this actually matches with the sign that you learn in about permutations. So, we will also see later how it matches, but now it is clear that indeed what is happening here. Okay. Whenever you switch two columns, you get minus sign out. Okay. The number of switching that you make is what counted in this sign. Okay. Again, the parity of that is counted, whether you are switching odd number of times or even number of times. So, that is what counted. So, now if you take this sign, which is a group homomorphism from Sn to naturally map to plus or minus 1, because determinant of identity is 1. Every time switching actually gives you either plus 1 or minus 1. So, you get a map from Sn to plus or minus 1, which is a group homomorphism. Then what will be the kernel of this group homomorphism? So, this is going to be those permutation in Sn such that the sign of that permutation is exactly even. Okay. So, that is exactly called alternating group. So, this is called alternating permutation, okay, which is denoted by AN. So, AN is a normal subgroup of Sn by the construction, because it is realized as kernel of this group homomorphism that is given by sign permutation. So, this AN now in terms of writing permutation as a product of cycles and all, we will see that it will be product of even cycles always because of this property. Okay. So, that will be proved later, but I want to introduce the alternating group as kernel of this sign homomorphism. Okay. I will stop here and we will continue with some more definitions in the next class. In particularly, we will talk about what is called direct product and internal direct product. Okay. So, I will stop here. Thank you.